All right, so if we look at the challenge problem for today, I can find it. We are talking about hybridization. So now we are talking about when we look at these three-dimensional molecules that we have, these shapes, and we assign locations for them in shapes. We know that we have this breakdown between where we said they were in the atomic orbitals and where those atomic orbitals are oriented, and our new location where we have these orbitals based on the molecular shape. Oh, my pencil's almost dead. Okay, so for this one, we're going to draw the Lewis structure of this CF2Cl5. So the first thing we do, just like before, is we put the least electronegative element in the center, which in this case would be this carbon, and then we arrange everything else around it sort of symmetrically. And then if we look at the total number of electrons, each one of these halogens, the fluorines and the chlorines, have 7. So 7 times 4 is 28, plus the carbon gives us a total of 32 electrons. So then if we go back and give everybody the octet, like it says, now we have 8 things around the outside, 8 electrons around each atom on the outside. 8 times 4 is 32. So this would be a good start. Then we have to look at formal charges. If we look at the fluorine as a valence number of 7, so 7 minus the lone pair, which would be 6, minus 1/2 the shared. So each one of these fluorines has a 0 formal charge. And then the same thing with the chlorines, they have 0 formal charges. And if everything on the outside is 0 and our total charge is 0, that means the carbon has to be 0 as well. So this would be the best Lewis structure for this C2 or CF2Cl2. So then we have to look at we want the molecular shape. So again, we look at where we have electrons around the central atom, and we have electrons, there's 4 places. All of them are bonded pairs. So when we have 4, the electrons is going to be tetrahedral, right? There are no lone pairs, so our molecular geometry is also going to be tetrahedral. And for this electron geometry, we would say that the bond angle is 109.5 degrees. There are no lone pairs, so then the bond angles down here are going to be 109.5 degrees as well. Okay. And then the last thing we want is the hybridization. The hybridization, again, is going to come from this electron geometry. We have to figure out where we put electrons, right? And in this, what we're going to do is we are going to mix together as many atomic orbitals as we need places to put electrons. So we have to mix together 1, 2, 3, 4 atomic orbitals. So we always start with the S, that's 1. Then we move to the P's, and we have a total of 3 there. So this would be, because it's tetrahedral in the electron geometry, the hybridization would be sp3 hybrid. So now we have this new set of orbitals around carbon that are no longer just s orbitals or p orbitals. We've mixed them together to come up with this new sp. So we've taken essentially the s orbital that we had and the p orbital, right? We added them together to get a new hybrid orbital, which we call the sp3 orbital. Right? We mix together the s and 3 of these p's to get 3 of these new orbitals that look like this, that are happen to be, we end up getting 4 sp3 orbitals, and their angle between them is 109.5 degrees. Right? So this is one way we've come up with to, because this one was a sphere, this s orbital was a sphere. The p orbitals were these dumbbells along the axis. So if we just relied on our atomic orbitals for this hybridization, we would see this new hybrid orbitals. Apparently, my sharing. Any questions on that?